This is Cybernetics for the Newtonian Diehards. Ross Ashby's book Made Easy. In 1947, during the Macy Foundation meetings of scientists in New York, Norbert Wiener presented a book called Cybernetics, or Control and Communications in the Animal and the Machine. Notice that cybernetics was not born as a science, but rather as a large field of knowledge helpful to many other sciences. Cybernetics connected two worlds, the mechanical and the living. The common link was a process called feedback, which had been present in the Watt governor since the steam engine and the Industrial Revolution. Once made explicit, feedback was designed into automatic controls and was a key idea at the start of the computer revolution. W. Ross Ashby, shown here, took cybernetics to a new level in 1957. He redefined cybernetics. He said, cybernetics deals with all forms of behavior insofar as they are regular or determinate or reproducible. It stands to the real machine, whether electronic, mechanical, neural, or economic, much as geometry stands to a real object in our terrestrial space. The subject matter of cybernetics is the domain of all possible machines, and it is only secondarily interested if informed that some of them have not been yet made either by man or by nature. What cybernetics offers is the framework on which all individual machines may be ordered, related, and understood. Perhaps you have noticed, perhaps not, but Ross Ashby's definition of cybernetics engulfs traditional Newtonian science methods and even quantum mechanics statistical methods with room to spare. More on this later. In his book Introduction to Cybernetics, Ashby says that the most fundamental concept of cybernetics is that of difference. Either that two things are recognizably different, as an apple and an orange, or that one thing has changed with time. Pen and paper machines will illustrate what change is about. Ashby builds pen and paper machines to illustrate change, one step at a time. Keeping the idea of difference in mind, he starts by telling us what a transition is. A transition is produced by an operator acting on an operand. For example, we have an operator called sunlight acting on an operand called the skin, producing a transition to a darker colored skin. Difference and change are present again when a set of transitions becomes a transformation. Ashby speaks of theoretical machines using a symbolic approach to machine descriptions. It is from these paper and pencil machines, mostly in matrix form, that he discovers the laws of control. Next, Ashby explains that any machine behavior can be described as a closed transformation. A machine can go from A to B, from B to C, from C to D, and then back to A. Think of a V8 engine with the pistons going up and down and intaking compressed gasoline vapors in the cylinders and then firing and so on. Ashby realized he did not have to deal with a real machine. He could replicate behaviors using transformations, or what I call pen and paper machines. This is how he reinvented cybernetics. As simple as that. Next, Ashby defines system as an observer-dependent list of variables that map into a single-valued transformation. He says, every material object contains no less than an infinity of variables and therefore of possible systems. Studying all of the obtainable facts of a material object is unrealistic, impossible. We pick and study the facts that are relevant to some main interest. For instance, in the physical pendulum, the variables that produce a conduct of interest are the angular deviation and the angular velocity. It is these varying states of the system that produce the desired singleness of behavior. Linking these two variables will produce the equivalent of a closed and single-valued transformation. By doing so, Ashby swept away the eternal philosophical question about the final essence of things. Things are many different things at the same time. You, as the observer, defines the system, provided you can show how your list of variables work together as a unit. With the new definition of system, considering its external behavior and its functionality, this opens the door to study systems as generators of probabilities. Here's an example. A roulette wheel produces many different numbers in one of two colors, red or black, after its spin, plus the green, 0 and 00. Trying to define a system of outcomes as a transformation sequence is impossible. You cannot guess the numbers or colors that will appear, but it is perfectly possible to determine the probability of the outcome for each spin. The probability is the important variable for this system, not the variable number or color that is generating the probability. Numbers and colors are not predictable, but the probability can be calculated. In addition to Ashby's external behavior definition, systems are usually defined from an internal perspective as a set of interrelated parts. These two definitions, internal and external, become complementary because the parts of a given system act as vectors that interact to influence the state of the system, which in turn translates into an external behavior. Here we see that a system is a set of parts and their interactions, and a system is the emergent result of its parts' interactions. None of a system's parts can do what the total system does. The external behavior of a system is a sequence of different recognizable states. For instance, look at the stoplight. From the red state, it changes to the green state, and then to the green-yellow state, and back to the red state again. Ashby then defines the complexity of a system as the number of different states it can show. In cybernetics, systems are never large because of their physical size, but because of the number of different possible states, their complexity. Ashby calls it variety. Here are some examples of differences in variety. It also speaks volumes about cybernetics' power as a language with enormous generality and applicability. Cybernetics is a lot like playing poker or placing a bet. You have to count and compute what are all the possible outcomes and then which one is the most likely to happen. Cybernetics typically treats any given particular machine by asking not what individual act it will produce here and now, but what are all the possible behaviors that it can produce. The connection between this approach to machines and information theory is important. As we shall see, information theory is characterized essentially by dealing always with a set of possibilities. Here is an example of how all possible behaviors of a fertilized egg get reduced to a very different outcome. From two very similar DNAs, you can get a gorilla or an amazing human being. Therefore, cybernetics was defined by Ashby also as the study of systems that are open to energy but are close to information and control. Another type of system is the black box, a system with inputs. The inputs can alter the internal states of its hidden parts and its external behavior, also called its output. That is what control is all about. Watch how the output and feedback result in a change in the input. Negative feedback takes an error signal to adjust the output until the desired outcome is achieved. Positive feedback accelerates the output. When confronted with a black box, you do not have to enter the black box to figure out its complexity or the variety it produces. Now we turn to Ashby's law of requisite variety. It says, only variety can destroy variety. In a system subject to regulation, the regulator must at least match the variety of the system in order to gain control of it. The variety of the system is the number of states that the system can produce. The regulator of that system must be able to match every such state in order to control the final outcome. For instance, to control the safety of a child, you must be able to neutralize every single dangerous behavior he may attempt. And the picture, of course, is an extreme case of control. Here is a graphic expression of Ashby's universal law of control. To control the system, the regulator must be able to amplify its control or filter the system's outputs. Here is an application of the black box in Ashby's law to management. Given that only variety absorbs variety, the control of the environment by the management is done in two steps. The manager controls the operation, and the operation controls the environment. In both cases, the variety is matched to reach equilibrium and control by amplifying control and by filtering incoming variety. You see, management is able to meet Ashby's law of requisite variety by any of two means: amplifying its own control variety, as indicated by the amplifier symbol, or by filtering the variety coming from the system as indicated by the symbol for filter. Both symbols or originated in electrical engineering. These two connections form a homeostat, a dynamic control loop or system with continuous reciprocal adjustments through feedback. Life is a continuous balancing act between interacting and sometimes opposing forces. Management cybernetics expresses this fact by showing the amplification and filtration process needed to achieve control and establish balance. An amplifier, as defined by Ashby, is something that, if given a certain amount, produces another amount. A classical amplifier is a sound amplifier. A small current from a microphone will turn into a large sound. There are many examples of controlled variety amplifiers. Police amplify their control capability using radios, guns, handcuffs, tear gas, fast patrol cars, and teamwork. In management cybernetics, the amplifying capacities of an organization are usually related to the product itself. A good product amplifies the client's own capacity to do something. Advertising is another form of amplification, as is word of mouth. Internal memos, rules, and punishment are forms of controlling amplification too. A filter is anything that will stop undesired input from entering the system. There are many examples of things that work as filters. Oil filters, sunglasses, admission tickets, job qualifications are just a few examples. Even your tongue and nose are filters. Cybernetics, we have said, starts with a universe of possibilities and finds out why only a subset has materialized in real life. Whatever reduces a system's possibilities is a constraint on that system. For instance, a chair is made of 4 legs, a seat, and a backrest. The individual freedom of the pieces are constrained to 0 when the pieces are hammered together. The world of physics and all of traditional experimental science is about identifying the constraints that nature imposes on matter and energy. Quantum mechanics does that at the atomic level using statistics. For instance, the properties of a hydrogen atom are its natural constraints. A hydrogen bomb destroys the constraints to produce huge amounts of energy. Ashby's path to information theory is amazingly simple. The number of possible states of a system is its complexity and also its variety. The variety sets the context that produces the information. No information is context-free. A yes or no does not mean anything unless you know the question or context or variety it is addressing. Ashby confirms this simple explanation. The information of a message is related to the existence of a set of possibilities, or the variety of the system in question. Therefore, the information conveyed is not an intrinsic property of the individual message. Every state of the system may have a different probability. It follows then that the greater the probability of a given state of the system, the lesser the amount of information contained in the message. A message saying it is now raining has provided little information if rain had a large probability. The amount of information is proportional to its newsworthiness. Measuring the amount of information of a given message is related to the set of possible messages. It is very convenient then to measure information content using binary digits. A 0 and a 1 are the elements of a binary digit or bit. They convey information about events or states of a system with equal probabilities of happening, as in a heads or tails throw. The longer chain of bits, the more information to be transmitted. Every bit doubles the amount of information it can carry. Again, the variety of the system is going to predetermine the amount of bits necessary to report any possible occurrence. Variety is also equal to the total information about the system. In practical everyday terms, consider a bit as a space for a 0 or a 1. So, the number of bits to report about a system is the logarithm base 2 of its variety. Therefore, if you want to inform someone about the state of the system, you need a number of bits equivalent to the logarithm 2 base 2 of the system's variety. For instance, to report who won a coin toss, you require 1 bit. To inform whether it is spring, summer, autumn, or winter, you need 2 bits. To talk about 8 different vegetables, you need 3 bits. For 16 candles, 4 bits. And to identify one of the 32 of Beethoven's piano sonatas, you need 5 bits. Thanks to Norbert Wiener, Ross Ashby, and other cyberneticians, most of today's science is done with a black box approach, especially when people build computerized models and manipulate the variables until the results match what happens in real life. Most science today is done under the cybernetic paradigm, not the Newtonian paradigm where the observer has isolated himself or herself from the experiment. Knowing the very basics of Ashby's cybernetics is of enormous practical use today. Thinking in terms of requisite variety, amplifiers, filters, and black boxes allows you to understand the exact nature of the problems before you. Ashby says at the end of the book that any problem is always a problem of correct selection. Today, you've made a good choice. Thank you.